In this episode of Thinking Through Autonomy, we talk to Sanjiv Singh, CEO of Near Earth Autonomy, research professor at Carnegie Mellon University, and editor in chief of the Journal of Field Robotics. His company makes some of the most advanced autonomous navigation systems in the world, and they work in vehicles ranging from Navy helicopters to drones. How good, you ask? Well, Near Earth was on a team in 2018 nominated for the Collier Trophy. That good. We talk about how to spin off university research and start your own company, lessons Sanjeev learned from landing helicopters autonomously, key technologies you need to understand that drive innovation in autonomy, key safety management principles, and understanding regulatory hurdles. Welcome to Thinking Through Autonomy, a podcast to help you understand the promise and impact of autonomous land and air vehicles in our world. I'm Ken Dunlap, managing partner of Catalyst Go, taking you on this journey. Hear and read more at thinkingthroughautonomy.com. Now it's time to take your hands off the wheel, foot off the pedal, hand off that throttle, and let's go. Sanjiv, welcome to Thinking Through Autonomy. It's great to have you here today.
Happy to be on.
Let's start right out by comparing then and now. At the start of your career in robotics and autonomy, can you kind of share with us what was that one problem that you as a young engineer thought, hey, this is never going to be solved? It's just beyond the capabilities of the technology and the software and what we know about autonomy.
I think one thing that we could not have imagined back then is that we would have commonplace use of self-driving cars and anyway, aircraft that would fly by themselves among the public anyway. There were discussions about grand challenges, but certainly nobody was thinking even of what we see today or we're on the verge of today as a potential at that time.
Well, does that mean when we think about the self-driving cars of today and the drones of today that are just on the edge of being ubiquitous in our world, does that mean there's not one grand problem left to keep them from being truly ubiquitous? Or is it just a series of little problems we're working on right now?
I think we fool ourselves in believing that technology is the key problem to be solved for autonomous machines to be ubiquitous, because it's always a mixture of technology, culture, and economics that says something about how these machines become integrated into our lives. So I can't think of a single, grand challenge or a single problem that if it were solved, then everything would be good.
So there's no silver bullet quite yet.
No silver bullet.
Okay. Well, you're coming off of what only can be described as a banner year in 2018. Near Earth was part of a team nominated for the Collier Trophy. And for our listeners not familiar with this award, it's the aerospace industry's equivalent of like the Nobel Prize. And previous recipients include, the crew of Apollo 11 and the Wright brothers, to just name a few. And you're in that really, incredibly elite group of nominees. And I'm just wondering, can you tell us a little bit about what Near Earth's role was in this effort?
Yeah, our role was to develop the perception and the planning for a full-scale helicopter to fly from A to B and fly safely and fly efficiently in all kinds of very difficult conditions. So that was the challenge that was posed to us at the start of a 5-year program, a big program that the Office of Naval Research put out, which was build the equivalent of a self-driving car, but only applicable to a full-scale helicopter. And it was interesting to see how that came about in contrast to the work that was done on the ground, because that spanned many decades on the ground, and then we were able to take some of those ideas and translate them to an aerial vehicle. So what we were doing there was taking many of the same ideas that we had been developing over decades for the self-driving car world, and use them in the context of a helicopter that would fly in a sort of a high performance kind of a setting.
And as I was watching the news reports about this, it left me with the impression that a soldier on the ground would just push a button and call the helicopter, and the helicopter would survey the area and decide where it should land. Functionally, is that really how easy it is now? Push the button and the helicopter will come and land?
Yeah, that's actually a simple way of saying it. Demonstrating a technology and then putting it into practice as a kind of an appliance kind of thing to the sophistication. So, for example, that you see in many of the self-driving cars, that takes a long time. So we did demonstrate the feasibility of doing this. The idea was that you could fly from A to B, and the vehicle would stay safe going from A to B, even if it had to encounter things that were not on its map and it hadn't planned for, which are mostly trees, wires, buildings, terrain that were unaccounted for initially. And then come in and land and make sure that if the site that it was supposed to land was somehow or the other different than what was thought about, then while it's coming in at a high speed, be able to survey the area, build a map, and figure out what's a good place to land and land.
What I want to ask next is, what is this magic sauce that Near Earth has that makes a relatively young company a big league contender just so quickly? What do you have there that's magic?
We never thought of it quite like that. I think if you're in the thick of the technology, it's just the next thing to do. But I think there were a couple of things looking back that helped us differentiate ourselves. The aerospace industry has not really developed the methods that the ground vehicle automation guys have. So when you look at autonomous air vehicles in the past, they typically take off from some known location, quickly rise to a level where there's really nothing there to encounter, and then do these very planned, scripted approaches to some other very well known runway. So that's a well understood problem, and there are a large number of unmanned air vehicles out there that are used regularly for civilian and military purposes. So what we brought was this technology from the world of self-driving cars, where the vehicle has to be very aware of its environment and then very quickly react in a way that it's cognizant of what the vehicle can actually execute. So if the autonomy system were to give the vehicle some command it can execute, that's no good. So it has to be a very close coupling between what the vehicle can do and what it's told to do. That kind of thing, coupled with a reaction to its understanding of the environment, is a set of technologies that we had been developing for many years. And I think this is what we brought into the aerospace world. That is called a secret sauce in some very general way. There was also this idea that we were willing to innovate, willing to rethink the problem in terms of the kinds of sensors that would be used, and be willing to take some chances in developing new ways of thinking about perception, unprecedented in this field. There were no prior instances of helicopters being equipped with perception systems such that they could stay safe, land safely. In fact, staying safe during cruise flight and then landing safely at a landing zone are two requirements that pull at opposite ends. One has to do with looking very far and being very, very sensitive to what's out there without a whole lot of precision, versus the landing scene, which requires extreme precision to be able to survey an area, to be able to gauge a slope that would be too steep for a helicopter to set down, or an object in the ground that would not be a good thing to land on top of. And that pull between these two kinds of requirements was something that we satisfied by iterating maybe a half a dozen times over the last 10 years or so.
Let's maybe step back a couple years in your career, because as we've heard, you really didn't start your career in aeronautics. You rather started your career in robotics. What is the attraction of autonomous robots and vehicles to this budding young scientist named Sanjiv? that came to Carnegie Mellon in 1985?
Well, I came to Carnegie Mellon because I'd heard that they were working on ground vehicles, autonomous ground vehicles, and I was initially just looking for a job in robotics, and it could have gone many different ways. Through serendipity, I got paired with Red Whitaker's group. I picked up the phone, and while I was finishing my degree at Lehigh in a robotics project, I did my master's thesis in, and I got Red on the phone. He was looking for somebody, and I came to work with him, and pretty soon I was working on an autonomous ground vehicle. So it was very simple at that time. I wish there was a grand plan, but it was an idea of being fascinated by robotics, or fascinated by the idea that we could program machines and then they would execute them. These plans that we were making, and do them in concert with their understanding of the environment. So it's very basic at that time. And then what got presented was a number of opportunities where we could use vehicles in the outdoors, outside the built environment. Okay, that was fascinating to me. That while a lot of robotics was happening inside in factory-like settings, that we might use robotics outdoors, where things are much more difficult. The ambient environment is not controlled. The scale is much larger. There's very little infrastructure you can put in the world. So all of those things were interesting to me. That's how it got started.
That has to be one of the luckiest phone calls you ever made because it leads you to Carnegie Mellon's Tartan racing team in 2007 that wins the DARPA challenge. That takes you to the epicenter of autonomous vehicles. And I'm just wondering, Sanjeev, you've had all of this experience with self driving vehicles. What kind of lessons do you take out of the ground vehicles and walk that over to what you're doing in the air?
So what I learned from being involved in the ground vehicle side is that robotics systems that operate basically in any environment, and if you're outdoors, it's so much more the case, is that they're more governed by the development cycle to do with the automotive world than they are to do with the development cycle in the internet world. Okay, this is like an important distinction that I think that many people miss, is that especially the people who have been investing regularly in internet software, that they think that robotics is just another kind of variation of that kind of world. Well, it's actually a very different world, which is more governed by physical systems, where the environment that you're operating in makes a huge difference. When we look at software development on that's purely on the internet, or that runs on a desktop or laptop or tablet, there's much less variation in what that software can encounter. And as is, those systems require a lot of testing. You can take any kind of software system. You can take a operating system that, after thousands of hours of testing, it's released to the world, and suddenly there's exceptions that people find to these things, and they need constant iteration. So that's in a world where there's very little variation. You get a particular kind of hardware, and it will run just the same in Estonia as it would run in Japan or the United States, right? I mean, there's not that much difference in the environment. Still takes a lot of testing and development to do that. In the robotics world, since we have physical systems, the environment plays a very crucial role, and it makes testing these systems and then saying something formal about them, that they would perform reasonably in all the kinds of conditions that you might encounter, very difficult, all the more difficult. And I think this is a lesson that I learned pretty early on, and that I think we should all be cognizant of.
Sanjeev, you've also worked on systems like Big Dog for Boston Dynamics. What did you learn about this kind of locomotion, from a machine that has four legs? And did that, are there any lessons there, to machines with wheels or machines that fly?
So first, let me be clear about what I did with Boston Dynamics. I was working on one project where we develop the perception system such that the legged vehicle could actually follow a visual target as it moved around. I've been fascinated by Boston Dynamics. They're just an absolutely incredible company that have sort of worked on what would look like extremely difficult problems of legged locomotion and been able to show extreme ruggedness and resilience to disturbances that a legged vehicle might be able to follow. In fact, the thing that's been very interesting to me is that they have developed a concept of what some people call mechanical feedback. And they've been able to take this mechanical feedback as opposed to visual feedback to an extent that they could show that the vehicle is stable through proprioception, basically its internal sensing of its joints and sensing of how it's oriented in the world just inertially, and use that to have a stable gait in very, very difficult kinds of settings. So that has been an absolutely incredible, unprecedented sort of innovation that Boston Dynamics had to work on.
Sanjiv, despite all of this success with things that are crawling, walking, or rolling, you become attracted to drones and air vehicles of all types, as we've heard, from something as big as a Navy helicopter to something as small as a typical drone. What encouraged you to kind of leave those wheeled and tracked disciplines and make you go after things that fly?
Yeah, it wasn't a an overnight thing for sure. When it became possible for us to have small aircraft that you could put computers and sensors on, that area was growing very slowly. So it wasn't like I saw something and I switched overnight. I was right there when it was possible to put a few hundred grams of sensing and computing on to an air vehicle, and then a few pounds, and then et cetera. But what fascinated me was that it was the third dimension we could use. What I'd seen with ground vehicles operating in sort of outdoor environments, cross country, not on roads, but just basically going through rugged terrain or just open rolling terrain, is that ground vehicles get stuck very easily by coming up to small obstacles that they have to negotiate. And so the way we've gotten around this is that we build machines that actually can surpass these things mechanically. So with very, very high clearance, you can actually go over all kinds of obstacles. But it occurred to me that there's always going to be some terrain that will pose all kinds of problems for our ground vehicles. Right outside my office at Carnegie Mellon was a steep drop off, railroad track, and then wooded terrain and then what you could see from there was the Carnegie Museum. And the Carnegie Museum could have been no more than a quarter mile away. And my thought was that if I imagined a ground vehicle from right outside my office going a quarter of a mile, without having any map, it would have been absolutely hopeless. But even if it had a map, a very accurate map, it would have had kind of a tortured kind of a route to take to get from out there to over to the Carnegie Museum. So I kept looking at the setting, thinking, only if you could just take to the air and fly, which would have been taken a few seconds. And I think this sort of very visceral kind of recognition that if you could use the third dimension, you could really surpass lots of things on the ground. And having had all these frustrations with ground vehicles not having perfect maps, and I realized that even in the ideal case, it was a very difficult solution in all kinds of terrain, and that in fact in the most common case, it was just practically impossible to do something that seemed like it should be so easy to do. And so air vehicles were clearly the answer. In the very early going, there were just a few people working in this area. We brought some technology and got some traction, and being willing to take some chances got us into some places where it was like a real opportunity that just sort of kept snowballing.
What then is the defining moment that tells you, I've studied and I've done research, I understand air vehicles. What's the moment that says, I need to take this out of the academic environment and I'm ready to commercialize what we know, what I know? How does near Earth autonomy start?
Yeah, that's also a very interesting question. I don't think it happens that crisply. It
Oh, but it makes
starts.
for a faster answer in the podcast.
Yes, that's right. That's right. So, I mean, it wasn't a moment where I thought, okay, the technology is ready to commercialize. A large opportunity presents itself. At that point, it's so big and so interesting that we think about all possible ways to do it, and becomes evident that we can't do it at the university. So there are not that many options, right? We could quit and join a large company and go after that. We could try to convince people at the university to take a chance on a very large project. In the past, when we've had the grand challenges, things that nobody has done before, it's taken quite a bit to convince risk-averse organizations to go for it when the rules aren't set. You don't know how risky the doing of these projects are. And what it came down to was there was an opportunity of a lifetime for me, which was to take autonomy to a full scale helicopter. It was a 5-year program, well funded. The only problem was that you had to beat everybody else to it. So the company is born really out of a kind of a frustration with not being able to work with the status quo. And only after the company starts, the business case kind of presents itself. And timing was such that a few years afterwards, we were just the air vehicle world went crazy. There was lots of stuff happening all over the place. It was not like that when we started the company.
On day one, you look around yourself and you say, here it is, we're at near Earth autonomy. How many people are in the room on day one with you?
Four.
Four. And from there, how many employees do you have right now?
This summer we're 85.
Remarkable story, Sanjeev. Near Earth Autonomy is the third company now that you founded. What kind of lessons are you learning? Is company two and three easier to start than number one? Is it easier to take a company from the academic environment and spin it off, or is it easier spinning off something that you have already as an idea? Are there any parallels in that, or any kind of lessons learned?
Near Earth is the third company, and there's a new company called Carta that also got started. And Carta is an interesting case because it actually spun out of Near Earth Autonomy. I think that the lesson that I've learned about commercializing technology is that first, there are lots and lots of ways to fail, right? But
Yeah.
the thing that drives technology is nuts, and this is a lesson that's hard to take. Is the most important thing that helps a company succeed is market timing. Okay, you can't guess that a priori, right? It only becomes evident in hindsight that okay, the market is ready for what you have. And I think that that's a risk that entrepreneurs have to take. A lot of technologists, including myself, tend to think about the technology first, how cool the technology is, and how many people think it's cool, and how much interest they're getting from the press or from possible investors who are approaching you. But in fact, I think that this is a lesson to learn: is that companies succeed based on how much of a market there is for the kinds of products there are. So it's easy for people, technologists, to be too early, to have a great idea but nowhere to go with it. That's one thing that became evident to me. A second thing that's become evident is that the team matters a lot. Of course, this should be very clear to most people that the synergy between the team that starts a company and leads a company, that is very essential to the success of a company. And I think that's borne its way out in the four companies that I've been involved in to date. The funding part, availability of resource is important, of course. Without these kinds of resources, it's hard. And how that plays out is, I think that if the market is stronger, then you can start out with a little bit, and then the market is pulling. There's lots and lots of opportunities, and if one of these things, or two of them, or three of them fail, there's always other opportunities to consider. If you start a company and it's, the business case is marginal, then I think it becomes very, very difficult to keep the thing going over time. And I think that is a difficult thing to sort of gauge at the outset. So I think these are the main lessons that I've learned and try to execute on as we go forward.
Great. Sanjeev, you have this company focused on autonomy, and I looked at the list of services you offer. You have mapping and surveying sensor solutions, obstacle detection and avoidance, landing zone assessment and selection, flight path planning, GPS denied navigation, all of which to one degree or another depend on this thing we call autonomy. Can you tell us a little bit about what it means to be autonomous? Because everybody's talking about autonomy on the television, when it comes to air vehicles. We see manufacturers that say, we have a truly autonomous vehicle, yet you scratch your head and you say, no, you don't. And they certainly don't have the same kind of capabilities that we're seeing in more advanced systems. What is autonomy? How do we put our arms around autonomy in air vehicles?
For air vehicles, there is a sense that of something called the inner loop. The inner loop is what keeps a vehicle stable and flying in a direction that you tell it over a very short period of time. You might be able to use this, layer some GPS waypoint following, and in some worlds, that is autonomy. Okay, so a vehicle takes off and gets up in the air and it follows some GPS breadcrumbs. And if you very carefully script your your flight path and there's nothing unanticipated along its route, then it could possibly fulfill its mission just by doing that. Okay, so the problem is that there are, in fact, in many interesting missions, you need to be able to fly close to things or to go to some places that you haven't been to before, which is to say that you cannot always carefully script the mission. And so it's necessary to put some sort of intelligent outer loop over this inner loop. So around the stability control of an air vehicle, you need to add some cognizance of the world, and that's where the autonomy comes in. So a very simple way of thinking about what autonomy is for air vehicles is that it is the outer loop around the inner loop of stability control for an air vehicle. Another way of thinking about autonomy is that it's all about contingencies. Now, apart from the world being different than you expect it to, you might imagine that the aircraft might have some trouble. It might have a problem with its fuel or its engine or some critical sensor, or it might encounter things like birds in the air. All of these sort of lead to it needing to deal with some rare occurrence that is not in the nominal plan. And for us to imagine that aircraft are going to be integrated into the national airspace, they're commonly operating without someone controlling them on a sub-second level. It is absolutely important that we have technologies that replace the kind of intelligence that a pilot would use to be able to guide the vehicle safely when these contingencies occur. So that's another way of thinking about it. Now, we've tried to boil it down into a few phrases that are easy to understand. So we say, for the most part, autonomy is about enabling a vehicle to fly safe, land safe, do it without GPS, even when things go wrong. So there are four phrases, very simple, but I think all the capabilities mentioned earlier sort of boil down to some version of this: fly safe, land safe, do it without GPS, even when things go wrong. And that's, in a nutshell, is what we think of about as aerial autonomy.
And we kind of touched on this, but I want to go into a little bit more detail. What are the key technologies that give these vehicles a sense of where they are in the world? The relationship between me as the vehicle and the tree across the street. Because clearly they have to see something. What is the technology you're using to position that aircraft so it understands where it is and what's around it?
So, okay, the two problems that we've been solving in robotics, ground or air, very general problems is where am I and what's around me? Okay. Now, when you have a vehicle that's operating inside a factory, you might add some infrastructure. Now you take it up in the air where the scale is much larger, the environmental conditions can be different. It can be day or night, or it can be a cloudy day or a bright day. This becomes much more difficult. So, if you think about the where am I problem, we look at two kinds of technologies. Also, there's an analog on the ground side, which is some sort of odometry, which is some kind of dead reckoning that allows the vehicle to use its internal sensors and also external sensors, like such as cameras, to be able to just count its steps, so to speak. Okay, so it can use an IMU and a camera to be able to determine that it's flying in a particular way. Now, this kind of thing works for a few seconds at a time. Maybe if you have very good IMUs, it could work for tens of seconds. But essentially, then you need some sort of a map update. Okay, that map update, or some sort of a position update. It might come from GPS if you can recognize landmarks, you can recognize the terrain, you can recognize a visual landmark of some sort. You can update your location based on that. So it's usually a combination of this, which is some sort of dead reckoning that's augmented with some update from some fixed thing in the environment. Okay. So that tells the vehicle where it is. If we can do that at extremely high frequency, fairly accurately, so that it's smooth, we can take sensor data that is coming from sensors such as LiDAR or even cameras and use that data, use this positioning to register this data into some sort of common framework. Why is that important? Well, at any given time, vehicle sensors are going to see like a snapshot, a little bit of the world. And typically, what it takes is some sort of collage of these sensors, a collage built out of sensor data for possibly a short period of time, some buffer that is right around the vehicle to be able to build a picture, sort of some sort of understanding of the world around it. And then when you can register this data together, you can have some sort of understanding of hazards in the environment and how to react to these hazards.
So, can I assume that everything you described relies somehow on AI? Is there a relationship between AI and these advanced autonomous capabilities? Or are we talking about two separate things?
Yeah, this is a tricky point because the closer you get to artificial intelligence, the less you see it as a monolithic technology, right? So I think what we see is that there are different kinds of things that people call AI. Certainly, the kinds of AI that are used to do data mining are different from the techniques we use. People used to say that artificial intelligence are just those data structures that we haven't fully incorporated into our commonplace usage. And I think that's probably the case still. So I try to stay away from this expression because there are very specific kinds of techniques that we want to use for different kinds of things. For the very, very lowest level, we want to think about how to represent the dynamics of the vehicle such that we understand what the vehicle is possible to do. So, for example, the vehicle, the dynamics are not symmetric. You can't go down or you can't go up. Every vehicle can't rise up in the same kind of fashion that it can go down because gravity is pulling, right?
Hmm.
But left and right, it might be able to. Might be able to execute turns with the same kind of maneuverability. So we try to think about how we can deal with these kinds of fine-grained representations such that you can actually execute them in real time. So I would say, for the most part, this is sort of creating its own branch of artificial intelligence methods that are able to help machines understand the environment and react to the environment.
I just want to close out this topic with maybe one more question, Sanjeev. Can you describe for the listeners what a typical mission would be for an autonomous system built around near Earth technology? What does that look like? What should I be imagining the capabilities of a vehicle that is truly autonomous?
Since much of what we do has to do with contingencies. Um, Sometimes a nominal mission is not an exciting one, or it doesn't show off all of what the system is capable of doing, right? But let me give you some idea about some of the stages of autonomy for through all the parts of flight. So before a mission starts, what we would do is specify to a planner, here is where I am, and here's where I want to go, and here are all the places for whatever reason I don't want to fly over. In national airspace, that would mean you want to stay away from airports, you want to stay away from sensitive government facilities, stadiums, things like that. Those are areas that you don't want an autonomous vehicle flying over for safety reasons. Before the vehicle takes off, it's going to plan a path that minimizes the risk of flying. And then it's going to look to ensure that along every section of the flight, if something goes wrong and the vehicle had to come down quickly, that there is a potentially safe place or multiple places to land. The vehicle takes off and it's going to be watching for hazards as it takes off. Okay, the world can change. The vegetation, buildings, towers, these kinds of things can be different from maybe the last time it operated in that environment. There is this idea that much of the risk is concentrated in the first 50 to 100 feet, from the environment. When you get above 100 feet above ground level, or what we say AGL, there's a whole lot less to worry about from the static world. In that case, now as the vehicle transitioned to what we call cruise flight, the biggest risk there is to deal with other aircraft that might be flying. There's always some aircraft that could be operating in that environment, and if you've done your job correctly with air traffic control, there should be nothing to worry about because these flights have been deconflicted already. But in fact, because things don't go quite as they're planned, you still have to be aware of other vehicles that might be flying differently, or people that are not they're not under the governance of the air traffic control. You might imagine all kinds of other aircraft, ultralights or general aviation. They proceed under the assumption that the pilot is aware of the threats around it and will be able to take the necessary precautions. Okay. The next thing we worry about is that if something goes wrong, then the vehicle has to decide how much time it has and use its understanding of the safe areas to land. It has to be able to evaluate the place that it's coming down to make sure it's landing safely. So if it's been told to land in a soccer field, maybe one side of the soccer field is okay to land, another one is not. It should be able to make that distinction and come down in that area such that it lands safely. Now, if no such thing can be found, then the vehicle should have cognizant that there are places that it's safe to ditch, such that it's only losses to the aircraft itself. When it comes into land in a nominal setting, we may have it landing in a place where it has some infrastructure there that's sort of like an ILS for drones that will help make sure that it lands safely and precisely. Before it lands, I should have mentioned this earlier, if GPS is out, then it has to recognize itself that GPS has been interrupted for some reason, either because of um, nearby terrain or possibly interference from other sources, possibly jamming by some other entity. So be able to guide itself in such a way that can still continue its mission. And then land safely in a way that a pilot would like. So as you can see, a lot of it is about contingencies. It's about planning for contingencies before you get going. It's a lot about safety. It's about minimizing risk before you get going, and then always be watching for the kind of very unusual case that something is different than what you would expect from nominal flight.
Wow, Sanjeev, those are remarkable capabilities. Thanks for outlining that for us. I want to change the discussion for the last couple minutes we have here and talk about some of the challenges that you potentially are facing just trying to experiment and test vehicles with all of these advanced capabilities. I mean, I'd have to think you're at the mercy of the legislative and regulatory process for a lot of the things you want to do. In fact, I also have seen that Near Earth regularly needs to file exemptions with the DOT to fly these vehicles. How do you view the current state of affairs with government regulation? Is that helping your operation or is it hurting your operation? Or is it not, a deal breaking factor so far?
Well, I'm one of the people who believe the FAA does us a great favor by keeping us out of trouble. I think that there are ways to test aircraft that both um, allow technology to be developed and stay safe. So I think that the on the on the air side we have an agency that is entrusted with the protection of the airspace and also the people that we overfly, and it's a very very big responsibility. As you can see, there are lots and lots of people interested in putting aircraft in the air, and there are lots of regulations. Here is the trouble, and I don't fault any entity for it, is that the technology we're looking at right now is somewhat unprecedented. It doesn't fall necessarily easily into the realm of an experimental aircraft in the usual sense of the word. So when a company develops a new kind of aircraft to fly, it's experimental till it has been certified by the FAA through a whole bunch of through a fairly extensive process to make sure that it's safe. That is one kind of process that is not quite the same kind of process that is needed to help autonomous air vehicles fly in the national airspace. Our whole community is trying to establish even the ground rules for how to think about autonomous vehicles. So there's a group that I've been tracking for a while. It's called GAMA, which is the General Aviation Manufacturers Association. They represent a consortium, an industry group of aircraft manufacturers that work together with the FAA to think about a roadmap of how we might sort of progress from fully manual vehicles, new kinds of aircraft that haven't existed before, to a case where they could be flown by a person who does not require a helicopter pilot's license to a place where they may be fully autonomous. So I think that the roadmap for testing air vehicles, autonomous air vehicles especially, is somewhat unclear. And it requires the entire community to come together to make this possible. I think the people who are frustrated by this process are the people who want this thing to go much much faster. And I think that we're not served by playing up those frustrations. Rather, we're served by thinking through what would we do if we had to think about making these aircraft safe. Now, there's a wide range, right? There's some somewhat arbitrary sounding kinds of milestones or sort of breaks there. For example, Part 107 has to do with 55-pound aircraft that are 55 pounds or lighter, and then everything above 55 pounds has another set of regulations in the United States. So I think we may want to think about where those breaks occur, because certainly flying something that weighs 55 pounds and flying something that weighs uh, 2,000 pounds is quite a different kind of an aircraft. So I think that roadmap on how to develop autonomy for aircraft is not evident right now, and there isn't a consensus. And there are people at NASA, the people at FAA, the people at the at Gamma who are working together to establish this some of this. It may not be happening as fast as everybody likes, but I think that if you're in it for the long haul, like we are, we find ways to test our systems within the current regulatory framework. Um, and hopefully, what we can see is in the next few years, with a large upswell of interest in this area, that we can, in fact, establish a roadmap to certify or to accept these vehicles. Part of the problem, and maybe belaboring this, is that there are processes like DO 178 certification for um, getting airworthiness of specific aerospace components may not be applicable. So new standards, not only a new sort of roadmap is necessary, but just even the standard for certifying systems that are non-deterministic, okay, is going to need a different process.
Sanjeev, as we look at this regulatory debate, in terms of certification of the airframes, airworthiness standards, certification of pilots, we know that there are people out there that are saying autonomous systems need to be treated differently. They need to have higher levels of regulatory oversight. They need to be in a special class. Do you think that helps or hurts the autonomous industry? Do you think there's some truth to the fact that these need to be treated differently for regulatory purposes? Where do you fall on that?
So I think that this is a question of cultural acceptance of what level of risk we're able to take. It's not a pure technological or economic kind of a question, right? I think that if you imagine that air vehicles become uh, reliable, safe, used commonly, autonomous air vehicles I'm talking about, then you have to imagine that the road from where we are today to there is going to take some failures along the way. So the question is, what kind of failures are we willing to accept? So, for example, for commercial aviation, the whole system should be certified to have no more than one Class A mishap in 1 million hours of operation. Okay, so Class A mishap is defined as an accident or a failure that causes more than, I think, $1 or $2 million worth of damage. And there are ways of mathematically thinking through this, right? So let's say we could do that with an autonomous system, even if we could think about these kinds of numbers. But where do we want to draw the line? That's not a technological or economic kind of a question purely, right? It has to do with um, cultural acceptance of these risks. And I think that that's not going to happen easily. So I think that this takes some time to be able to bring a level of risk that's acceptable to be able to reap the benefits of this. And I think there are a couple of ways to do this is to show safe operation in areas that are intrinsically less dangerous. So, I would imagine that lots long hours of operation in rural areas or in areas that are uninhabited, this would give people a lot of assurance that you've seen these vehicles can operate eh, successfully, or they have some mean time between failures that common people can understand before they're allowed to operate in urban areas, and especially. So I think there's ways of thinking about this risk that could make the population, the general public, much more comfortable with the idea of risk, and eventually it's a cultural question.
And in terms of risk, do you envision a future where companies that operate autonomous vehicles have to receive special certifications, have to comply with certain safety measures, much like we do with airlines right now? Is that something in the future?
I would have to believe that's the case, right? I mean, we have to be able to understand risk. We have to be able to insure against that risk. Unless we can understand the risk, I don't see how we could insure against it.
Sanjiv, I just want to wrap up this podcast with two final questions. The first involves the future of near Earth autonomy. We know that Boeing has led your Series A funding, and I'm wondering, does that mean your future has already been written? What's the future for near Earth?
So I think that our investment says little about a prescribed future path rather than an interest in these kinds of technologies. I think the future is very open, and where I think our challenges are is to make sure that we get traction with real commercial opportunities in a sustainable way. We could go out and get further funding uh, using a very optimistic understanding of where the commercial opportunities are, and fail because we get the timing completely wrong. So I think that the challenge for us is to connect with commercial opportunities in the short to medium term, rather than in a very long term sense. And that picture is constantly evolving. Our understanding of where the use cases are, where we can get traction, is a continuously evolving story. I think I might have mentioned this to you, Ken, and you can keep this in if you like. That there is this car museum across the street from us. You see 100 different cars in there at the turn of the 20th century, and very few of them made it. So clearly, the technology was there, right? But there were some of those cars. They got an economy of scale and some use case that was able to meet a need of the moment in a way that was sustainable. Rather than being worried about it, I'm inspired by the idea that we could find such traction to meet a need, not of someday, but in the very near future.
And I'm going to leave that in because I think that's truly inspiring and really hits the point. Let me ask you one final question. We've talked about your company, we've talked about autonomy, and I want to talk about you. And this is the last question for you, Sanjeev. So in 2012, Time magazine described you as an amateur writer, photographer, and cook, and oh, yeah, by the way, a roboticist. If you had to choose between receiving a James Beard Award for your cooking or the Collier Trophy, which one of those are you going to choose?
That's great. Um, when I wrote my PhD thesis in robotics, I was thinking about how many people would read my PhD thesis compared to how many people would download my cookbook that I had created very early in graduate school. And I was very clear that my PhD thesis would get an order of magnitude less reads than my cookbook at that time. Okay. Now I certainly am hoping that there'll be more opportunities for the Collier Trophy.
Okay. Well, that was kind of the litmus test of the morning here. I can't thank you enough for being on Thinking Through Autonomy. This has been just an incredibly enjoyable conversation, and I wish you and Near Earth much success in the years ahead. And I know we're going to be reading and hearing more about you. Thank you so much, Sanjeev.
It's been my pleasure.